Yeah, camp on everyone. Let's start off. Yeah, camps on everyone. Great. Let's start off with a question. So let's say we have two people here, A and B, and there is a mirror here. The height of this person is 2h. The height of this person is h. This distance between them is h. This distance is also h. So the question is, this person B is looking into the mirror. So find the minimum length of the mirror. If B can see, yeah, B can see himself and A completely. Neglect the distance between the eyes and the head. So you can assume the eyes are exactly on top of the head. Yeah, let's get this. So there are two people standing back to back, and the B is looking into the mirror. He wants to see himself in the mirror, and he also wants to see the person behind A in the mirror completely. Matlab, uh, when you go to your washroom and look at yourself in the mirror, can you see your legs? You can see your face, right? You can't see the legs. When you go to a shoe shop and when you're trying the new shoes, right? When you look at, they have a different mirrors if you observe. You can see your shoes there. You can't see your face. Observe it. So you need a certain length of a mirror and in a certain position so that you can see yourself completely. So we need the minimum length. Hope the question was clear. Give it a try. This is a little decent one at a plain mirror. And others do keep your cams on. Arya, Devanshi, Obia, Param. So, cams on. Hope the question was clear. Yeah, everyone should try to solve the problem instead of combing your hair and playing with your hair. So do give it a try. So let's go one at a time. So forget about A first of all. Just ask yourself for B to look at himself. See, when do you say I'm looking at you, what do you mean by that? The light rays from the person should hit the mirror and reach your eyes. So if B wants to see himself, now this would be a straightforward CT equation. If I took take about B, now I'm ignoring the the height between eyes, but imagine we still have some position there. So this is the idea there. So the light rays from the mirror should hit and reach your eyes. The light rays from the leg should hit and reach your eyes. That means the mirror should be from here to here. So this is your minimum case where the light rays from the leg and your head are hitting the edge of the mirror. Is that making sense? So you need at least this much. Now we know this angle and this angle are equal. Let's call it alpha and alpha. So if I take this distance to be x, then this distance is also x. And here also, if you take a bisector here, then this height will be y and this height also will be y. And you can clearly see here, this distance is y and this distance is x. So 2x plus 2y, that will be the height of this person h. X plus y is h by 2, that is the length of the mirror. So that means for B to see himself, the minimum length is h by 2. You need at least half of your height to see yourself. Anything less than that, you can't see your full image. But there is still one more. And again, this half of the mirror, you can't keep wherever you want. The top of the mirror must be exactly on your eye level. So there is a position there. Because you're saying minimum, there is a position there, right? So yeah, anyway, we're ignoring this top part of the height. So it should be exactly, the mirror should start from the head of the person. This is a standard result at a CET level equation. So for B to see himself, the length of the mirror is h by 2, starting from his eye level. So this is the scenario for B to see himself. Now B also wants to see A. Now understand it here. So when you're saying you're looking at A, what you're looking at is actually the image of A. So when you have the mirror here, so if A was here, so A ka image would be somewhere here. So what you're looking at is actually, so from this part, they should reach your eye level, and from here, it should reach your eye level. So this is what is actually happening. The light rays from A is hitting the edge of the mirror. They bounce and they go back like this. So this person will think this light ray is actually coming from here. Similarly, this light ray is hitting here and bouncing off this way. Are you getting what is happening there? So light rays from A are hitting the edge of the mirror and they're bouncing off to the eyes of the person B. So B will think, okay, this guy is A now, the right side. So basically, you're looking at that person there. This distance was h. This distance was 2h. That means this distance also will be 2h. And if you notice here, the light ray should go from the edge of the mirror, right? You can make this a triangle. So if you make this a triangle, you will clearly see. So this height is 2h. This distance is 3h. Your mirror is somewhere here at a distance h. We can clearly see it will be in the ratio of what, 2 is to 3. So this guy should be 2h by 3. Is that making sense? So for B to see A, you need a mirror of 2h by 3. But again, you have to be careful here. Now, till here it looks fine. Now, this is the trap part. If you look at the eye level, that starts at the center of the mirror. Means we need a mirror of 2h by 3, where the center of the mirror is at the eye level. For B to see A, length of the mirror is 2h by 3. Right? And midpoint of the mirror is at eye level. Now, most people will do what? The previous one is h by 2. This is 2h by 3. So 2h by 3 is greater than h by 2. So answer is 2h by 3. But the position matters. Midpoint of the mirror is at eye level. Now, if you combine both of them, now see what will happen. So for B, to see himself, you need a mirror of h by 2 starting from your eye level. In order to see A, we need a mirror of 2h by 3. Midpoint is eye level, meaning we need a mirror of h by 3 on the top, above your eye level, and h by 3 below your eye level. So what we need is actually a mirror of h by 3 above your eye level and a mirror of h by 2 below your eye level. So the length of the mirror will be 5h by 6. Is that clear, everyone? That what makes this a good one. The position of the mirror. All clear with this? Just plain mirrors, a little geometry there. So any doubts on this? So length of the mirror is one, and second thing, the position also, where you keep also matters. Clear? Akanksha, Anvita, Shaurya, clear? हो गया? Clear हो गया? Trishi, got this? Utsa, Sudiksha? Great. Next thing. Number of images on an inclined mirror. So if you have two inclined mirrors, how many images will form? So if you have two inclined mirrors, the image will be at an angle theta on either side of the mirror. I'll show you how it looks. That means if this was the mirror, this was the object and this was theta. Last time I showed you, the image should be on the other side where the mirror will be the bisector. So this also should be theta and this should be the image. So this is how the images will form. So basically, if you look at them, they will form a sector kind of thing of 2 theta there. Now, if you put two mirrors, all images that form, so you will get an image of an image. Because a mirror cannot differentiate who is real and who is virtual. All it will see is the light rays. Will lie on a circle. Because they all are equidistant from the center of the mirror, from this corner. So center is point of intersection of the mirrors. So if you have two mirrors, and let's say angle between the mirrors is theta, and your object is somewhere here. So what would happen? So using this as a distance, if you draw a circle, now this O will form an image somewhere here. That will be I1. O will also form an image somewhere here, I2. Then I1 will form an image here somewhere, I3. I2 will form an image again here, I4. And I4 will form an image, I5. And so on. Like an image will form another image, and all these images will fall on a circle. And how many images will form? If all are forming on a circle, right, you can clearly see each one will form a sector kind of thing, and each sector has angle theta. So 360 by theta is the total number of sectors. In that, there is one object. So 360 by theta minus 1. So that is how we get a formula there. So let me write down that also. And then we'll actually try to see what is the location of these images. So case 1, if 360 by theta is even, then the number of images will be 360 by theta minus 1. This is independent of position of the object. You can keep them anywhere between the mirror. This is the number of images. So for example, if you have two mirrors, 90 degrees, let this be M1 and let this be M2. So if you have an object here, this is what actually happens. So the light rays will bounce like this. So you get an image here, I1. And now what happens? These light rays, which are bouncing off, they will hit this mirror and they'll bounce off here. So M2 will think light rays are coming from I1. So if I just put one more here. So they will bounce like this. And when you extend them, you will get one more image here. Let's say I2. So I2 is the image. This is the image of I1 in mirror M2. Because see, mirror M2 will think light rays are coming from I1. It does not know who is O directly. Meaning, yeah, O, it will also form a directly image there, but and I1 getting and similarly, some light rays will hit this mirror and they'll bounce off to this thing. So they will form one more image. So we will see that. So you'll get an image of an image. And this will just keep on happening. At some point, right, images will start overlapping. So you'll count them as one. Case 2, if 360 by theta is odd, then the number of images is 360 by theta minus 1. So if object is on bisector. So if your object is in bisector, answer is 360 by theta minus 1. It doesn't matter whether even odd or anything. But the answer becomes 360 by theta if object. So if the object is not on the bisector, that is when you have to be careful whether it is odd or even. Right? So, but let's say example, you get something like this. 360 by theta is 6.93. And then you take the greatest integer 6. So because there's no meaning of 0.5 or 0.8 image, you take the greatest integer. So clear, don't round it off to the next one, take the other integer, because a fractional image doesn't make sense. So this is your general formula there to find the number of images. If you want to find the location exactly, let me show you one example how it works, and then I'll ask you something on this. So let's say we got a two mirrors. Object is here. Let this angle be alpha, let this angle be beta. and alpha plus beta is theta. That's your angle between the mirrors. So this is how the rule goes. You keep adding theta to add theta to get an image in the next mirror. I'll tell you what it means. And when you keep doing this, finally, you will get some alpha final, beta final, plus theta 360. If you get this final angles, the sum is 0, meaning sum is 360. That means the last images coincide. Okay, so how do we do this? This is images in M1. This is images in M2. Look at the idea here. First thing, let's call this thing M2 and M1. So the first image, M1, where will it will form? So this is the object here. So this will be your I1, and where will it form? It will form at an angle alpha from the mirror M1. So we start here with an alpha. So that means the first image in M1 forms at an angle alpha from M1 mirror. Is that making sense? The meaning of that? Next thing. Now, what will this I1 do? This I1 will try to form an image in M2. But what is the angle between I1 and M2? The angle between I1 and M2 is alpha plus beta, which is alpha plus theta. So I1 will form an image in M2, somewhere here I2, where this angle will be alpha plus theta. You're getting it? It'll form on the other side. So I'll not draw it here, but let me show it like this. So when you add theta to this, you will get an image alpha plus theta. You're getting what is happening? So you are doing one thing. Now, this image which we got, I2, with an image of alpha plus theta, now I2 will again form an image in M1. Now what is the angle? Alpha plus theta plus theta. So again, you will put a theta here. So this will be alpha plus 2 theta. Meaning this image in M2 formed an image in M1 at an angle of alpha plus 2 theta from M1 mirror. You're getting it? You keep playing like this. Then again, you add in theta. This will be alpha plus 3 theta and so on. Similarly, when you do the other side, beta, I'll show you with numbers that will make more it easy. So beta will form an image here. This will be beta plus theta. This will form an image here, beta plus 2 theta. And you keep doing this. You have to make sure you don't exceed 180 degrees. So we get finally you'll get some alpha final here and beta final here. So do this till 180 degrees on either both sides. Now, after getting this, then we will do alpha final, beta final, theta if it is 360 images coincide. Roughly got the process. Let me take some numbers. You will understand this more easily. Let me make a simple one. Perpendicular mirrors. Let the object be here. Let this angle be 30 degrees and let this angle be 60 degrees. Right? So here angle between the mirrors is 90. Let this be M1, let this be M2. Images in M1, images in M2. So how do we start? So this was your alpha, this was your beta. So alpha was 30. Then add 90 to it. you'll become 120. Add 90 to it, you'll become 210. So we don't do that anymore. So 210, so we don't do this. So we stop it there. You don't cross 180. Start from here, 60, add 90 here, 150, add 90 here, done. So you're again crossing. So we don't do anything more. So that's it. So basically I had to do only one time. So what is the meaning of this interpretation? So let's write for each one here. So 30 degrees is what? This is an image here, I1, which you're getting at an angle of 30 degrees. So this is your I1 image, 30 degrees. So I1 is an image of O in M1 mirror at an angle of 30 degrees from M1. That is how you read that whole angle as, at an angle of 30 degrees from M1. Perfect. Now, when you added 90 here and this became 120, so this guy was image of I1. On which side it is? It is on M2 side, right? Image of M1, I1 in M2 at an angle of 120 degrees from M2. Meaning this guy, I1, let's call this thing image as I2. So you will get an image I2 from this M2 mirror. You have to put 120 degrees on this side. So somewhere here. This is I2. This will be 120 degrees from this side. Is that making sense how we are interpreting it? Now, one thing we know, all of them lie on a circle. So let me just draw a circle first. So I2 must be somewhere here. Great. I took a story got over because after this, if you add 90, you're crossing 180. Next thing, this guy is 60 degrees. Again, we add 90 to this. That will become 150. So let's call this thing as I3 and let's call this thing as I4. Again, you know how to read this. So what is I3? I3 image is in M2 at an angle of 60 degrees from M2. So that thing is somewhere here, I3 at an angle of 60 degrees from M3. I4, this is the image of I3 in M1 at an angle of 150 degrees from M1. Meaning from M1, I have to put 150 degrees. So this will be 90 there. How much will that be? So we already know this is 120. This was 90. The remaining is 150 actually. So I2 and I4, right? They'll be side by side. This is 150. 200, 270, yep. Making sense? So I4 and I2 are overlapping at the same place. So we can clearly see here. So this is your alpha final and that's your beta final. So alpha final plus beta final plus theta, which is 150 plus 120 plus 90 is 360. Yeah, that means I3 and I4 overlap. I2 and I4 overlap. Kind of making sense what we did. You're getting how we are framing the images. So this is just a way of writing it. It looks big because I'm explaining. Exam, you can do it faster. So you just have to keep adding 90, 90, 90 till you reach 180. And all you need to understand is this. What is the meaning of 150 here? Where is 150? On M1 side. Where is it coming from? It is coming from here. I3 say. Matlab, this 150 was the image of this guy I3, right? And it is at an angle of 150 degrees in M1. That's the interpretation there. Roughly got an idea, right? Let me give you a question. That's the best way to learn. I can explain it this 10 times. You will feel like, oh, something is weird. If you do it on your own and mess it up, that's the best way to learn. So you guys give it a try. You just give me the images. If you can put them on a circle. M1, M2. Let's say this is the object here. This is 20 degrees and this is 30 degrees. Find the images. So theta is 50 degrees. Locate the images. See, if they just ask you find the number of images, this is all headache. Just use this formula and finish it off. If they ask you the exact locations on a circle, then this will work. Try. Let's see. Let's see this thing. Same story. M1, M2. I'll call this alpha, I'll call this beta. So this is 30, 30 plus theta, 80, 80 plus 50, 130, 130 plus 50, 170, 180. Right? So we don't count this. If you hit 120, you're gone. It should be less than 180. Because see, think about it logically. When you say 180, you're simply saying the images form exactly plane to the mirror. That's not possible. You can't have light rays parallel to the mirror. So 180 is not acceptable. The other side, we have 20, that's your beta. So 20 plus 50 is 70, 70 plus 50, 130, no, 120. 120 plus 50, 170. So that's acceptable. So let's name them. Let's call this guy I1, I2, I3, I4, I5, I6, I7. There are 7 images. Now let's put them on a circle. So you have a circle. These were the mirrors. M1, M2. The object was somewhere here. Great. Where is I1? This is how you read. I1 is in M1 and at a 30 degrees from M1. So this is your I1 at 30 degrees. Great. Where is I5? I5 is the image of M2. It is 70 degrees from M1. See, forget about who's and what. So these angles will simply tell you there are images in M1, 30, 70, 130, 170. You can just keep drawing them. So this 70 guy, which is I5, so it is somewhere here. Not up to scale, but this is 70. That's your I5. 130 is I3. That is 130 from here. So from here, 130 you have to draw. That should be somewhere here. This angle is 130. And then it is 170. So that's pretty close to here. I7. This is 170. Uh, what are the final angles here? Alpha final plus beta final plus theta. Alpha final is 170, beta final is 120, and theta is 50. This is 340, less than 360. So yeah, the final images are not coinciding. When you actually draw them, you will realize they're not coinciding anyways. Let's see the other side, I4. I4, now these angles are on the M2 side. So 20 degrees from M2. So this is I4 and this is 20. Then 80 degrees from M2. So M2 say 80 degrees. So it will be somewhere here. This was 80. And that thing was 120. I7, I6, no? I6 would be, I don't know, you can just draw it somewhat like this. This will be like 120. There, those are the 7 images on a circle. Are you getting how they're going? So basically, these angles will tell you. So from M1, draw 30, 70, 130, 170, you'll get 4 images. On M2 side, draw 20, 80, 120, you'll get 3 images. You're done. That is how we can look at it. Is that making sense? That was easy. We'll try one more. Since you got it, you can just draw it fast. So on a circle, you can tell the exact locations there. This is M1, this is M2. Let's say this is 50 degrees and this is 10 degrees. So again, theta is 60 degrees. Get the images. Another 30, 40 seconds and I'll show you. You can verify your answers. Okay, let's see. Let's. So this is alpha, this is beta, M1, M2. So your alpha was 10 plus 60, 70 plus 60, 130 plus 60, 180 you're crossing. So we will not do it. 60, 10, 70, 30. We are done there. Great. 50, 50 plus 60, 110. 110 plus 60, 170. We are done there. And we can clearly see alpha final plus beta final plus theta 130, 170, 330, 360. So these two guys are actually overlapping. Great. Let's call them something I1, I2, I3, I4, I5, I6. I3, I6 overlap. So technically there are only 5 images. Now when you put them all in a circle, M1, M2, the object was here. So I1 is somewhere here, 10 degrees. I5 is I5 is 110. So that would be somewhere here. I3 would be 130, so that would be here. On the other side, if you see the images, 50 would be on M2 side, so that would be somewhere here. I'm just drawing them roughly there. So this would be 70 here. I6 will be 170 here, so this guy would be I6 again. So 1, 2, 3, 4, 5 images. Clear with the positioning? Any doubts on this? So this is how you can locate the position of the images. Finding number of images is the easier one. If at all by chance someone decides to ask you, give me the position, this is how you handle them. Any doubts on this? Great. That's what happens when you have two mirrors. Now, what happens if you have incomplete mirrors, or what if a mirror is broken? Then what happens to your image? So what happens with an incomplete mirror? Let's say there's a big mirror there and you're standing in front of it. So it's not a single light ray. There are bunch of light rays which are, all these things will, there are a bunch of light rays there. Now, if someone decides to break the mirror, and let's say you stand in front of a mirror, not in front, the mirror is here, mirror is there. But now you will think like, oh, nothing is happening. But in reality, if you see, your image will still form there. The image will always form as if there is a full mirror, but the catch is this. The light rays which are going this way, they are bouncing off. So it will appear they're coming from here. This thing last time I taught you, field of view. So only people here can see you. Your image is still there only. They will think there is an image there. Only this person can see your image. This is your field of view. The image does not vanish, and all these light rays which are there, they will just go here as if nothing happened. So if someone is standing here, he cannot see anything. He will think there's nothing there, nothing is there. This guy will say there is an image. So if you have a mirror, even a piece of a mirror, extend the mirror, make it as big as possible, draw the image, It will be at the same place as a full mirror. The only difference, there are actually two differences. One is the field of view. Second, because the number of light rays reaching your eye has become less, the image will be less bright. Did you ever notice this? Uh, you go to a shopping mall, you get a dress, you try it in the trial room, it looks good. You come home and try that, and it feels, yeah, I took this dress, it was looking good, but now it looks little weird. Ever felt it? Boys will understand this better. You're at home, you look at yourself in the mirror, you look like a jungly person. You said, oh, I should need a haircut. You get to the saloon there and you're sitting there and waiting for your turn, and you look at yourself in the mirror and you think like, I'm not looking really that bad. Kabhi hua? The reason is this: in that saloon, right, the mirrors are big. In your house, the mirror was small. So the number of light rays reflecting on the mirror and coming back to you are less. So the image has a less contrast. But suddenly in a saloon, right, the big mirror will make your image bright, and that's why you look better. The same way in a shopping mall, trial room, did you see how many mirrors are there? Front, back, left, right, up, down, everywhere there are mirrors only. And upar se kuch orange color lights. So you really don't know what color you're looking at it also. So that's the reason the dress in a trial room will always look better than the same dress at home. So one way to do is what? Get big mirrors in the house. So then also you look good. But that's the main thing there. So part of a mirror behaves like a full mirror. It doesn't matter where you keep that part of a mirror. So just extend the mirror, make it a full mirror here and find your image. So if you just want to find the location of an image, it doesn't matter. So part of a mirror or a lens. This is valid even for lens. If you remember, when we find image, we take only two light rays, but in reality, there are infinite. Or a lens forms an image. At the same place as a full mirror or lens with a decreased intensity. That is the catch. So you need to be in the field of view to look at the image, and the image will be less bright. So that's the story about which the mirrors which are broken. So there was a question like this. You are a wildlife photographer and you want to take a photograph of a zebra. And you go to a certain place thinking there are zebras and you find a white donkey. So there is a beautiful white donkey. Right? So now you're thinking, how the hell will I get a zebra ka photo? Then you come up with a brilliant idea. You say, okay, I will take my camera lens there, right? And assume that white donkey is very stationary there. So you take a black color marker and on your camera ka lens, you put some black lines. So that when you see through the lens, it looks exactly like a zebra. You're getting the story? The white donkey is there, stationary. You took a camera ka lens and you put some, you're looking through the lens and you kept some markers, black lines. It started looking like a zebra. Now, if you take a photograph, you'll get a zebra. What are the cats? What will you get on the photograph? No, the thing is, no, people who are wearing glasses or something, you're just looking at it. Imagine if I put my finger like this in front of this thing, will I still see you full image or will I see half of your image has got cut? The problem, I can still see you full, right? I don't see half of you. So the idea was this. What you did, you took the lens and you actually shaded some parts here, isn't it? That means you have broken some part of the lens. Can I say like that? So what will happen is this light rays from every point on the donkey will pass through the remaining part of the lens. So what you get is still a white donkey, which is less bright. You get in the catch. But what if you insist, no, no, I still want a zebra. Paint the donkey. You have to stop the light rays coming from the donkey. So if you paint the donkey, not red, black, now light rays don't come only from that place. So now you might get a zebra. So So if you break the lens in half or you paint the lens in half, you're not going to affect the image quality. It's like I have two eyes, I'm looking at you. If I close the eye, I'll see only half of you. Does that make sense? If I squint my eyes, I'll see only the little part of you. I'll still see full, right? So closing the lens and decreasing the size of the lens does not change the position of the image. What changes is the brightness. Anyway, so that's one there. So what about this guy? Suppose if you have a situation like this, so we have a mirror M1, we have a mirror M2. This is the object, this is a 90. If you extend this, they will form a 90-degree here. So there is no mirror here. Now, how many images will form? So we have two perpendicular mirrors and someone broke a part of it, and this is how it looks. How many images will form? Let's see how many answers will be there. So even though from the point of view, right, 90 degrees should give you three images, something happens here. You should understand the image formation thing there. This is what is happening. If if you look at the light rays here, these light rays are going here, and these light rays are going here. So when you extend them, yeah, you'll get an image I1 here. If you look at here, there is not a single light ray which will go from M1 to M2. Making sense? There is not a single light ray which is going from M1 to M2. So M2 does not know who is I1. Similarly, you will get an I2 here. Similarly, not a single light ray from I2 will go to M1. So M1 does not know who is I2. So I3 doesn't form only. But all you need to do is this. If you extend the mirror little mirror, if you extend here, now suddenly these light rays will bounce here and go to M2. Now suddenly M2 knows there's an I1, it will create one more image. Are you getting the difference? For a mirror to form an image, you need to have light rays. So if you break a mirror like this, there are no light rays going from one mirror to another. So in this case, you get only two images. So the answer is two images. So all you need to do is extend the mirror a little and you'll get a third image. Light rays from M1 never reach M3 and vice versa. Therefore, I3 never forms. So there are only two images here. Because if you go back to the story here, this is what I told you. The reason you get this image is because this I1 is, the light rays are going and hitting there. So actually, let me write this as I3. I didn't draw it properly, but yeah. Everyone clear with this stuff? Any doubt so far? Next thing. Now, that's about plane mirrors. Next thing is parabolic mirrors and spherical mirrors. So if you have a parabolic mirror, you know what's a parabola. And, now if you send parallel light rays, so that focus we keep saying now that is actually for a parabolic mirror. It was never for a spherical mirror. So all this astronomical, telescopes and all, which they use in the observatories, they are actually all parabolic mirrors. These light rays which come from very far, when they hit this parabolic mirror, they get focused. And this light is so weak, so you need to collect a lot of light basically. So they actually keep this telescope focused in one point in space for days. They take something like crores of photographs. And from each photograph, they collect the pixels which are good and then they reconstruct the images. So a lot of software goes into it. Uh, so that is where the tech actually went, and people realized this is a really good technology. They took it and they kept it in your phones. You ever tried this burst mode in the phone? It just takes 20-25 photographs and selects the best one. You have all these features in the phone. So most of the things that we use, right, were actually developed for something else, and later on they became all this stuff. So if you send parallel light rays, they hit the mirror and they meet at the focus. Any parallel light ray, they will meet at the focus. Vice versa, if you keep a bulb at the focus, you get a parallel beam. Next time, if you get a chance, look at Enfield ka headlight. Enfield ka headlight, right? It looks like a parabolic thing. Or even this thing, your dish TV antenna is there, which looks like this. That's not spherical. That's actually parabola. And you must have seen that transponder, right? You have something like this here. So the idea was this: the signals will hit here and they'll meet at the transponder. So if you just want to mess with your neighbor, all you need to do is take this transponder and move it a little. And yeah, the TV signal will be a little bad. But anyways, vice versa in 3D, right? If you put a bulb at the focus, so this is your focus. So you get a parallel beam, so the light can go really far. So this is the property of a parabola. But parabolas are difficult to manufacture and they're expensive. I mean, until unless you really want that kind of a precision, so it's always about that. Among all the subjects that is there, the most powerful subject is economics. So it's always about cost versus effectiveness. If something can work, right, 90% as good as the best, but the cost is only 1/10, that will always win. Right. So then what we do? We created spherical mirrors because these are easy to manufacture. But they have a problem. If you take a spherical mirror and if you send a parallel light rays, they all don't meet at the same point. This we saw in one of the equation, r by 2, 1 minus sec theta. So what you get here is a distorted image. The parallel rays do not meet at one point. This is called a spherical aberration. Aberration meaning error. Spherical, it is an error because of being spherical. So, not exactly like this, but the pictures would look something of this sort. People with glasses, right? If you remove your glasses and look at a bulb, how do images look like? They don't look like clear. They look like a blur, isn't it? Or even during rainy season, if you look at the bulbs outside through a glass full of, the water droplets, you will see that blur. And this is how the images look like. Isn't this how it looks like for people without glasses? So if you have a good enough eyesight like me, -5, right? And you plan to kill me or something, the best way to is take me and throw me on a highway in the night. The problem is when that vehicle, right, switches on that headlight, right? That light doesn't look like a single spot. That thing looks like a blur. So I don't know whether a motorcycle is coming or a lorry is coming. You can't tell the difference. Like it's very bad. It happened with me once when I was in 12th standard. I was in the, I stayed back in the class. I had my glasses from 6th standard. Okay, so ancient person I am. Uh, People used to call me Four Eyes in school. Now it has become pretty common. Half the people in the class, or more than half, have glasses. But when I got my glasses first time in my 6th standard, it was a big deal. My mom started crying. My son has become blind. I said, I'm not blind, yeah. Right? My mom and dad started fighting with each other. And my dad was like, I told you, it is all because of you he became blind. He's like, not because of me he became blind. I said, yeah, first of all, you fight if you want. Don't call me blind for every damn 2 minutes. And the reason they're fighting was this. When my mom was pregnant, that when she was carrying me, she wanted to eat Karela. Someone told her, if you eat Karela when you are pregnant, the kid who is born will have an eyesight ka problem. And my dad remembered this after 12 years when I got my eyes checked and got an eyesight. They started fighting for that damn thing after 12 years. In this process, they started calling me blind. Yeah, it was a mess. Went on. 10, so 12th standard, what happened? That day I was stay back in the class. Kuch to ho gaya, the glasses fell down and they broke. It was almost evening 6:37, already dark. I had to walk 1.5 kilometers to the bus stop. It was hell. Crossing the road, I don't know what is coming. I reached the bus stop. I couldn't see the, and my eyesight is very high, -5. So if I remove my glasses, I can't even see, like, I can't even figure out who you are 1 meter far. Your face looks like a blur to me. So this is how it looks. So difficulties of people with eyesight and glasses. Anyway, so that's the thing there. So then what do we do for this? So we do an approximation. So how do we construct this? You take a spear and you just cut it. When you cut this, you get a part of a spear. This is the pole. This is your center. This was your radius. This thing here is called aperture. So aperture is the region where the light rays enter from. So radius of curvature of the mirror is different. Radius of aperture is different. So be careful with the terminology there. So you must have heard na lens ka aperture karke. So that is the area through which the light rays enter. So this is smaller. This is the radius of the aperture. So don't get confused between both of them. They'll sometimes say radius of aperture. People think that is capital R. This line CP is your principal axis. So aperture is the area through which light enters. So now when you take this, if you silver it on this side, so if you coat it with a silver oxide or something, this becomes a concave mirror. So it's like there's a cave. If you silver it inside, this becomes a convex mirror. So manufacturing them was easy. But then still, we still have our error here. So what we do is this part. We already wrote this in the last class. Just copy paste it. Where are you? This guy. So we do an approximation. You take paraxial rays. So once you take paraxial rays, now suddenly you can approximately say they meet at the focus. So still there is an error, but and it is fine. Matlab that much our eyes can adjust and work it out. So the glasses you're wearing, right? If you actually see, if you actually take this glass out and if you actually make it into a sphere, this will form a sphere of around 20-30 centimeters. So all the light rays entering through your glass are actually paraxial rays. They're very close to the principal axis. You're getting it? So the glasses you are using, they have a big radius of curvature. So it's like this is the big sphere, and your glasses are simply this size here. So for the light rays entering, like I said, right, it doesn't matter how big the lens is, the image will form at the same place. So all the light rays entering through your this glasses are actually paraxial rays, so it works out. Clear with this? That's the theory there. Now, next thing we're going to do sign convention. That's the most important thing. And like I said, ray optics may the two most important things are that sign convention and the formula. If you know this, you will get it. So let's have a break. Come back by 9:45. We'll continue from then. Any doubt so far? Come back by 9:45. Yeah, comes on everyone. Let's start off. The sign convention. Now, this we will follow for everything: lenses, mirrors. So there are two types of sign convention. One is your Cartesian coordinate thing, and another is following the light ray. We will follow the light ray always. That's more convenient. So we'll stick to that. But in case you have learned something else in your classes and you're okay with that, follow that. Getting it? There's nothing wrong like that is right and this is better. This is what I feel it is much better and more convenient. The direction of light ray is always taken as positive. The direction of the incident rays. So from the object, when the light rays come, you follow the light rays, and so you go with the light rays. Whichever direction the light rays are traveling, you take that as positive. I'll give you examples. So the direction of incident rays is taken as positive. Second thing, all distances are measured from the pole or the optical center of the lens. All distances above the principal axis are positive. All distances below principal axis are negative. Others, do keep your cams on. U is your object distance. V is your image distance. R is your radius of curvature. F is your focal length. So these are the four things you will see. Great. Let's take an example. The lens and the mirror, the previous same thing which I took before. You know the story. The letters will go from here. Let's say they're meeting somewhere here. This is I1. Then they hit the mirror. Then they bounce off. This is I2. These letters come and meet here, and they again converge here. This is I3. And at this point, right, the letters will go away. They'll not meet anymore, and you're done. Great. Now, we'll ask one at a time. So first thing, the light rays are going from object to the, you follow the light rays. So first we'll ask the lens. So lens is L here. Object is here. The I1 is here. So we know who is the object, who is the image. First thing, what is the direction of light rays? Light rays are going from left to right. So this is the direction of light rays. So we will take that as positive. When I'm doing for a lens, I don't care what the mirror is doing. Now, second thing, distances are measured from the lens. So we are taking this point as origin. And from the origin, the right side is treated as positive. The left side is treated as negative. That's the meaning of it. Now, what is the object distance? Object distance is O to L, but which way? On the left-hand side, minus OL. Where is the image distance? Right-hand side. So plus Li1. So when you, whatever the formula that is going to come, when you substitute the values, this is what you have to substitute. Minus OL and plus Li1. Great. Then you ask the mirror, mirror, what do you think? Who is your object? Who is the image? So for the mirror, now I1 is your object and I2 is your image. So letters are going again this way. We measure the distances from the pole of the mirror. I'll call it M. So the right side is positive. The left side is negative. So for the mirror, if you ask what is U, it will say minus Mi1. This is my object distance. V is plus Mi2. This is my image distance. Great. Now the letters are going back. So again, you'll ask the lens. For the lens, I2 is your object. So letters are going like this. This is your I3. So this is the direction of light rays. See, the lens doesn't care whether I2 is real or virtual. It will always say like, oh, letters are coming from I2. This is the direction of the incident rays. Should always see that incident ray. How are the light rays falling on the lens of the mirror? That means from this logic, and the lens is the origin here, this is your positive and this is your negative. Now your object distance is minus Li2, image distance is plus Li3. Are you clear with this convention? You follow the light ray. You just keep moving with the light ray. The advantage of this thing, the radius of curvature of a lens or mirror, right? It remains same whether you keep it left or right. There is another convention called Cartesian coordinate. I don't like it. That thing, the sign keeps changing whether just because you keep the lens in left and right, the whole sign will change. So it can get confusing. This thing you're just following with the light ray. Any doubts on the sign convention, please ask me. This is really important. All you need to do is mess up one sign and the whole question goes for a toss. And the same convention we'll use for lenses and mirrors and everything. You just keep following the light ray. When you talk about lens, don't talk about mirror. When you talk about mirror, don't talk about lens. So that's the best part. They're like three independent things. They don't interfere with each other. Next thing. U and V ka to aa gaya. Even for radius of curvature, we have sign convention. For example, let's say we have a convex mirror. And let's say the radius of curvature is 20 centimeters. Now, if your object is here, the light rays are coming this way. So this is the direction of rays. So even radius of curvature will have a sign convention. So this is positive. This is negative. So this is the thing you'll ask, where is the center? So for this convex mirror, this is the center, which is on the right side. Therefore, radius of curvature is plus 20. That is how you do it. For example, if you have like this concave mirror, and let's say radius is 10 centimeters. So if you have an object here, light rays will go to the right side. So this is positive. But where is the center? Center will be somewhere here on the left hand side. So here the radius of curvature for concave mirror is minus 10. Are you guys getting this? How the radius of curvature will change? So you have to see where is the center. Is the center on the left hand side in the negative x-axis or the positive x-axis? So this was your negative. So even radius of curvatures will have radius of curvature, the sign convention. What about a lens? Suppose if I take a lens like this, let's say this one R1 is 20 and let's say R2 is 10. And let's say object is here. Now what is the sign convention? Which one is positive? Both are positive or negative. What is R1, R2 ka values? This is what you do. First of all, light rays are going this way. So this side is positive. Okay. Now, this is what you do. Take for R1, extend this. So the center will be this way, positive side. So R1 is plus 20. For R2, extend this, make a full circle. The center is on the left hand side, C2. Therefore, R2 is minus 10. So for a lens, both the sides, radius of curvature, signs will change. Again, depends on sign convention. So you have to make a full circle and see where is the center. So it's always about the center. Let's say R1 is 10 centimeters and R2 is 5 centimeters. Again, it all depends on where is the object. Huh? Suppose if the object is here. Now can tell me what is R1 and what is R2? Light rays are going this way. This is positive. So R1, if you put a circle, center is on positive axis. For R2, if you put a circle, center is on the negative axis. So R1 is plus 10 and R2 is minus 5. Clear with the sign convention? That's how you get the sign convention for lenses and mirrors ka radius of curvature. So step 1, let the light rays go and hit the lens or the mirror. See which way they are going, left or right or up, down, whatever it is. That is positive side. From the pole or the optical center, the origin starts. From there, whichever side the rays are going, that is the positive x-axis, other side is the negative x-axis. If you have a lens, we have two curves, complete a circle. See where is the center, positive x-axis or negative x-axis. Done. Positive, the positive radius of curvature. Negative, negative radius of curvature. All clear with this? Now, we don't need the derivations for these things. They're really not that important. They have a lot of approximations, so they really can't mess up with anything. And the biggest approximation is paraxial rays. So you'll just write the formulas and we'll go ahead with that. For spherical mirrors, radius of curvature is R. If this is the object, it hits the mirror. This is the image. One by V plus one by U is equal to one by F. That's your formula. You need to write, remember them. You can write it down. F is equal to R by 2, the focal length, where R is the radius of curvature. Magnification. M, which is the height of the image by height of the object. Is V by U. These are the three formulas there. Now you have to be careful here. This U, V, R should be taken with sign convention. Second thing, this is valid only for paraxial rays. Third, this is valid only if the object is on the principal axis. Yeah, if it is not on the principal axis, we have ways to do this, but you can't use this formula directly. These are the three things you have to follow when you are using these formulas. Put on the formulas. We'll do a few problems to get used to the formula, and then I'll show you that ray diagrams and all that stuff, which I'm pretty sure you studied in school. Object is between center and focus, image is there, between focus and pole, image is virtual, all that stuff. You'll see that also. But before jumping, we can do a few questions before that. I'll copy to the formulas. Great. Let's see a question. We need to get you used to that sign convention as fast as possible. That we can do, that the things are taken care of. Because whatever you learn in mirrors, everything is applicable in lenses, exact same ideas, only the formula is different. Is 20 centimeters. We have the object here at 30 centimeters. Find the image. Find the position of the image. Sign convention, formula, nothing much. Done. Let's see. Step one, get your sign convention. So however the light rays is going, so light rays are going this way. So I'll show you for now, but you have to get used to it later on. You will get used to it. It just takes time. So meaning from here, this side is positive and this side is negative. Great. And where is the center? Center is somewhere on the left hand side. So U. Write it down for a few times. You can write down the value. So U, object distance, object is on the left hand side minus 30. Radius of curvature, center is on the left hand side minus 20. Focal length is r by 2, that is minus 10. V ka value we need to find. Apply the formula. 1 by V plus 1 by U is 1 by F. That would be V is equal to 3 minus 2, 15 centimeters minus. The minus and indicates the image is on the same opposite side of the incident rays. This is how the picture looks. So this is the ray diagram. Having a diagram is important. It will give you visually that feel what is happening. Actually, I can draw it here only. So this is what was happening. So these light rays are going here and hitting, and they're coming and meeting somewhere here. This is the image. And this distance was 15 centimeters. Got this? Same story here. Light rays are going to the right, so this is positive. The U is minus 20. R is plus 20. So focal length is R by 2 is plus 10. Substitute in the formula 1 by V plus 1 by U is 1 by F. So V is equal to 20 by 3 centimeters. Plus indicates image is on the right hand side, meaning these light rays went here and they bounced off like this. And when you extend them, the image is forming somewhere here. This is virtual. That is the meaning of this. Plus, it is on the other side. Light rays cannot meet on the other side. They appear to meet. This is a virtual image. All clear with the sign convention? Next one. Convex mirror, 20 centimeters. We have a thin rod. The length of the rod is L. The distance of this end of the rod from the pole of the mirror is 20 centimeters. I can call this B and I can call this A. So this rod AB is along the principal axis. Case 1, L is 20 centimeters. Case 2, L is 2 millimeters. Find the length of the rod's image. Let's see how you approach this. How do we approach this? Now, remember the formula I taught you is for a point object. Out of nowhere, suddenly I gave you a rod and I'm asking for the image. So the idea is this. If I can find the image of B and if I can find the image of A, from there, can I say the logic like, wherever I get A and B ka image, remaining all must lie between those two extremes? Is that logic making sense? So there is no need for me to find each and everything. Find the images of the extreme points, and you can argue like everything else is in the middle. So the distance between the two extreme images is the length of the rod image. So let's do the first case, 20 centimeters, meaning B ka distance is 20, A ka distance is 40. So find A ka image, B ka image. Now get it. So that's how you approach that. So if you find final image, if you find images of A and B, so images of other points must lie between them. Should I show you? People are tired today. Are Harshita exhausted? It is raining a lot. That's why people don't feel like studying anymore. Till last week, you all are crying, oh, it is so hot. And today it is raining, oh, it is raining. Nothing keeps you guys happy actually. If it rains, it's a problem. Doesn't rain, it is a problem. Let it rain. There's no water to drink. We have only like what 7% of water supply. If it doesn't rain for another month, we'll start leaving the city. It'll become a desert. Unfortunately, it is not raining the place where it needs to. So let's see. The second one is also a good one actually. So we just need to find the images of A and B. So if I take the case one, this is 20 centimeters. So first of all, for A, how are the lighters going? Lighters are going to the right side. So right is positive. So for A, U is minus 40. Radius of curvature is plus 20. Focal length is 10. So 1 by V plus 1 by minus 40 is equal to 1 by 10. So V is equal to 8 centimeters. For B, U is equal to minus 20. Radius is equal to 20. Focal length is equal to 10. Are you guys unable to type kya? You guys are typing here only or typing somewhere else? Because I didn't get a single answer from any of you still now. So I'm getting a feeling that you guys are typing to the other chat box, I guess. Okay. So yeah, you have to type there. I'm wondering why I'm not getting a single answer. You're typing to the co-host. No, it was my mistake. I was the host and co-host today. ठीक है. I think I changed it now, but anyway, I'm just saying here, type there. I was wondering why I'm not getting answers for this thing. Why is it so difficult? You guys did all that integrations and potentiometer, and this you're struggling. I was worried. ठीक है. So 1 by V plus I just said hi, type it to that. So minus 20 is 1 by 10. And this guy is how much? 20 by 3? Yeah, you're done. So A ka 20 by 3 is 6.66, right? So B dash will be somewhere here. A dash will be somewhere here. That means the entire rod ka image is this guy. And what is this length here? So this was 20 by 3 and this was 8 centimeters. So therefore A dash, B dash will be 8 minus 20 by 3. That is 4 by 3 centimeters. All clear with that? What about the second part? It is 2 mm. How do you handle that? Point to 2. Someone did get something. Now listen to this thing. Now that image is so small, what you can do is this. So 1 by u plus 1 by v is 1 by f. Differentiated. Now if you differentiate this, we get minus du by u square minus dv by v square is minus df by f square. This guy will be 0 since f is constant. I end up with dv is equal to minus du into v square by u square. So the idea here is, what is u? U is the object distance. So what is du? Du is the length of the object, isn't it then? Since AB is so small, if this is u, then this will be du, na? Because the length of the object is so small, I can say du is the length of the object. And dv is the length of the image. You're getting what we're doing? So this is what I was saying. I was saying like, let this distance be du and this distance was u. So what you're finding is du. Yeah, and once you got that, and remember, this is valid only for very small objects because du and dv are very small things. If the object was 20 centimeter, 10 centimeter, don't use this. Very small, like at least 100 times smaller. That's the preferable thing. So we can clearly see L, which is 2 mm, is much, much smaller than 20 centimeters. Works out. So first, let's find the Vega value there. So you can, this is how the picture would look basically. The rod is so small, you can treat it like a point object, which is at a distance of 20 centimeters. You can treat like a point object. So 1 by v plus 1 by u is equal to 1 by f. So v will be 20 by 3. Substitute here. So dv, du will be 2 millimeter. V square will be 20 by 3 whole square and u square would be minus 20 ka square. 20 goes off, we'll get minus 2 by 9 mm. Minus indicates the image got flipped. So AB became BA. Is that clear, everyone? How you handle the small images? You don't like that? You can take it as 20 and 20.002 and use binomial approximation. You'll still get the same thing. So you still follow the same process, like find the image for A, find the image for B, and do all that stuff. Lengthy, but this is a really good one. If they make things very small, this is the technique you use. And everything you're learning here, exact same stuff, you will learn again in lenses. The techniques are exactly same. Only difference is the formula there. All clear with this? Let's see one more. We got a convex mirror, radius r. We have a plane mirror. You kept an object here. Oh, the distance between the plane mirror and the object is x. The distance between the plane mirror and the pole of the convex mirror is y. And when you look at this, you observe there's only one image. Normally, if there are two mirrors, you should see two images. But for some reason, you're looking at only one image. Find the condition if there's only one image. This is the kind of a question you'll get in mains. Find the condition if there is only one image. नहीं Param. So the first, नहीं Trishi. You have to get a relation between X and Y and R. Ray. So the reason why you're getting only one image, that is only possible if both the images are overlapping, isn't it? R is x square minus y square by 2x. So you are saying if x is equal to y, Harshita, then your radius is becoming 0. Would be 0, nothing wrong with that, but maybe you're right only, I guess. Let's see. R is becoming 0, that matlab the mirror couldn't be a curved mirror anymore. X square minus is right over here. I think that looks right. You also got it right, Harshita, but नीचे x नहीं होगा, I guess y होगा वो. Let's see. So what was the idea there? So you can get only one image if both the images overlap. That was the main logic there. So images due to plane mirror and the convex mirror must have overlapped. That's why you're only seeing one. Okay, so if this was x, the image also must be at x. So this is where the image must have formed due to the plane mirror. That means this distance is x minus y. That is for the convex mirror. So for the convex mirror, u will be minus of x plus y. V is the image distance, which is plus of x minus y. Hope the sign convention is fine, and f is equal to r by 2. There, that's the main idea there. So from the plane mirror, it will form this distance, and this distance must be equal. So that is x and x. But this Beechka distance is already y. So that distance from the pole, remember, for a convex mirror, distance are measured from the pole. So pi is x minus y. So 1 by v, which is x minus y, plus 1 by u, which is minus of x plus y, is equal to 1 by f, which is r by 2. Just put them in the formula there. Simplify this. How much is this? X plus y minus x minus y. That will be 2y by x square minus y square is 2 by r. Yeah. X square minus y is equal to r. So if you satisfy this condition, you'll always get only one image. All clear with this? So that's an easy stuff. Next thing. So that's a little bit on formulas there. Now let me show you those pictures and tracing of images. So how do you, this is important. When you get a lot of theoretical questions, this will help a lot, tracing of images. Sometimes, questions would be theoretical. how is this image forming? If that happens, how does this look and all? I'll show you those things also, maybe in the next class, but you should know how the light rays trace. So normally, right, you have four special light rays. First thing, if you send a parallel light ray, it passes through the focus. Next thing, center is there. If you send a light ray through the center, it will come back. It will retrace, it will come back the same way. If you send a light ray through the focus, it will become parallel. If you send a light ray to the pole, it will reflect in such a way, this angle and this angle will be equal because the principal axis will become the normal. Got this? So these are the four light rays. So whenever you want to find an image, you choose any two light rays from the object, see where they meet, and that is the point of intersection. That is how you trace the images. Now, this part you studied in school, so I'll just use them directly. Then have a look at this. So the first one, object is at infinity. So light rays are coming parallelly, they will meet at the focus. The image is real, inverted, and diminished at the focus. You guys learned this in school? Second thing, object is between infinity and C. So the light ray C, one parallel ray is going like this, and this ray pole meeting like this. So the image is real, inverted, and it is between center and F, diminished. Just have a look at this. Next thing. This is even more variations here. Have a look at this. So the object is at center. So image will form at the center, real and inverted. So these properties are important, how it looks. Object is between focus and the center, real, inverted, and enlarged beyond center. Placed at focus, image is at infinity. Object is between focus and pole, this is virtual. So in concave, right, this is the only case where you'll get a virtual and erect image. Look at all the 6 cases. You will never get a virtual, you'll never get an erect. This is the only case you get virtual and erect. This is how they'll play with, the questions and theory. We will see few of them later on. But I'm sure you have seen this stuff in school, but have a look at it. Yeah. That's for concave, and interestingly, convex, right? There are only two things. In a convex, you'll always get virtual for a real thing. There are only two cases here. Light rays are coming parallelly, they'll meet at the focus. Any other light rays here will always form an image between pole and the focus. It is always virtual, it is always erect and diminished. Clear with this? Let's see how they will frame a question on this. Let's see one thing there. We have a concave mirror. So we have an object here, which is going with a constant speed u at a height. So it is above the principal axis and it is moving parallel to the principal axis. Yeah, rays are paraxial. It is close by, but it is not on the principal axis. Principal axis from minus infinity to pole. So as this object is traveling, the image will be there. Can you draw the path of the image? So if this object travels in a straight line from here to here, what will be the path of the image? Now, these things you can't solve with the equations if you don't know those 6 diagrams. If you don't have an idea how it looks where, then you're gone. Try. This is a pretty good one. Draw the path of the image. Did you guys get it? Now see, how to draw this, I'll tell you. Instead of looking at the the whole object, right? Let's treat it like this. So basically, when the object is going, so I will say, let's say we have some arrows, okay? So let's say this is the some arrow there, one. Let's put some points also here. So let's say this is the center, this is the focus, and this is the pole. So we have one arrow at infinity, one arrow between center and infinity, same height, one arrow at center, one arrow between center and focus, one arrow just before the focus, one arrow just after the focus, one arrow somewhere here, and one arrow exactly at pole. So we have 8 arrows like this, all same height. Now, if I ask you, find the image of these 8 arrows. First thing, the guy at the infinity will form an image at the focus. So this arrow will be here, 1. The second one, image will be between center and focus and diminished. So it would be something of this sort. This would be arrow 2. Arrow 3 will be at the center. It will be somewhere here, same size. Arrow 4 will be magnified, somewhat like this. Arrow 5 is almost at the focus. So this is gone to infinity. Once you cross the focus, the arrow 6 will be an virtual image, but you're still very close to the focus. So the arrow 6 will be somewhere here, infinity. Arrow 7 is virtual, so it will be somewhere here. Arrow 8 is at the principal axis, it will be at the same height. Now join the head of the arrows. Now if I join the head of the arrows, so kind of, isn't this how the velocity looks? That is how the particle is traveling. And here it is coming back like this. That is the path of the image. Is that making sense, everyone? So seeing it every time becomes difficult. So these are all the cases, right? You're at infinity, you're between center and infinity, you're at center, between center and focus, just before focus, just after focus, between focus and pole and at the pole. If you can draw these 8 arrows, then you will get this thing. Is that clear? Last one for the day. So the same logic, can you do it for the convex mirror also? Same story, the object is coming from infinity with speed u. Draw the image. Finish up, last one for the day. This is going with some speed u parallel to the principal axis till the pole. Get the image. We can send a virtual object, but it looks weird. If I say it'll break the mirror and go inside. So don't worry about it. We'll draw the graph of it in the next class, but yeah. Let's see. So again, same story, but luckily here, right, you don't need to put so many arrows there. You're at infinity, you're anywhere here, you're at the pole, you're done. That's it. There are only 3 arrows there. So if you're at infinity, so it's 1, 2, 3. So the 3 will be at the pole only. This will be the focus. And this will be somewhere here. So the image will be like this, everyone. It will be going down like this. Got it? It will start at the focus and then the path would look something of this sort. So you know how they can ask questions then? Then they will say, someone kept a square in front of a convex lens, a square. Then they'll ask you, how will the image look like? The image would be little diminished here. This is how the image would look like, isn't it? Yeah.
सर वो हमें कैसे पता चलेगा कि इट्स अपवर्ड कॉनकेव और डाउनवर्ड कॉनकेव?
तू बताओ.
सर आई डोंट नो.
You can think. Upward कैसा होगा रे God? You are tending towards this height. You cannot exceed this. How can the slope go up? As you
ओके.
get closer and closer to the pole, should tend towards this flat line, na? An upward concave will never tend, ना.
यस सर, गॉट इट.
मतलब तेरा ए बोल रहा था ना तू.
यस सर.
As think about it, from infinity you travel till here, you will travel from focus to pole, meaning at infinity if you travel large distances, here you travel small distances. So from there you come to the pole, you are moving a finite distance, so the function should tend to something. All clear with this? There. So this is the where I'm saying theoretical questions, you need to know how the picture looks for each and every. Okay, that will wrap up for that. We'll see you again next week. And like I said, do remember to finish your current backlog. Don't keep any backlog because after next week, you have to start doing ray optics also. Right. And there's a test online tomorrow. So make sure to give it. So any doubts, anything else, please stay back. I'll free to leave. I'll see you again next Tuesday, same time. So take care. Stay safe. think I lost the host, I guess. Where is this recording?